graphene, most people know graphene for its high electromobility, but because of the zero band gap, it is a non-ideal semiconductor for switches. To open up a band gap, it is important to reduce line edge roughness and scale the width down to 10 nanometers. And to obtain this band gap, our method was spacer lithography, and as you can see, it is the most efficient to scaling the width down and for it to be very smooth in the edges. These are other methods used in the past, and spacer lithography is really the most efficient. At the beginning of the summer, we started by finding the best selectivity with the silicon and the nitride. We start by depositing 180 nanometers of silicon dioxide for spacer sidewalls, and we add a chrome mask, which is going to help with the anisotropic features, so the sidewall is straight and we can avoid a facet. Spin with positive resists, expose and develop, and we get all the way to etching the silicon dioxide, and we get our spacer sidewalls. We deposit our silicon nitride for our spacers. What we found throughout the entire summer is that the amount of nitride deposited is directly proportional to the spacer thickness obtained. So we started with about 50 nanometers of silicon nitride deposited, and we would get about 55 nanometers thickness of spacers. So we used many different etching rates and times to see which one's going to be the best for our spacers and sidewalls. The selectivity that we got through our calibration was about 2 to 1 or 3 to 1 silicon to nitride. Ideally, we want a higher selectivity, maybe about 4 to 1. Hopefully we kind of obtained that with our final sample. After that is complete, we look through the scanning electron microscope and see which etching rate and time gave us the best sidewall. Note that it's about 167 nanometers tall, and that is because it goes through a high temperature process, and the height kind of gets a little shorter. So this is the one we used. This was the best sidewall we had. And for example, this one was over etched, and it's also very, very rough. So just kind of wanted to show like the good one and the bad one, kind of. The spacer width, these are both good spacers in like the smoothness, but the only thing is the thickness. So like I said, we started depositing about 50 nanometers, so we got a very like thick spacer. And then we went down to 40, and we got about 39 nanometers. For our final one, I deposited 30 nanometers of nitride. After that is complete, we also want the silicon nitride etch to be close to perfect. So what we want is for it to etch all the way to the silicon dioxide, but not over etch or not under etch. So what we did is change the power and the plasma density. Changing the power helps with the anisotropic features, and changing the plasma density helps with the cleaner tail, meaning the cleaner edge, a smoother edge. So you can see we thought that high power and high plasma density is going to be the best, but we found that medium power and high plasma density was our best match. We looked at the SEM picture as well as our color reference. So after our calibration is complete, then we finally start actually working with the graphene. We start by a small layer of silicon dioxide that's going to help reflect the graphene so you can see it through the optical microscope. And using the tape method, we exfoliate graphene, and what we're looking for is at least 20 microns of graphene. Now, I actually had to look for the graphene and write down where it is. We had our a coordinate system so I could find it and write it and put it on a layout. That was probably the hardest part of my project. But here's a picture, and this is actually really, really good. It's probably maybe 1 or 2 sheets of graphene, and it was, I think it's 40 microns. That was really perfect. It's the pressure applied when we're putting the tape on the wafer is really important. You don't want to put too much pressure, you're just going to get graphite, and you don't want to put like hardly any pressure because you're not going to get any graphene at all. The problem we came across was the tape residual. Because our sample goes through a high temperature process, it would create a bubble and it would explode, and that would get rid of the graphene, and then everything's gone. So the solution was 1165 cleaning overnight or for 1 hour under 70 degrees, and then putting in the furnace for annealing. We also played with soluble tape, and we also changed the temperatures and the time for the annealing furnace, but those weren't really as efficient as these two put together. And looking for the graphene in a lot of wafers is really very time consuming. We had a protection layer so that when our graphene goes through our plasma and everything else and the high temperature, it doesn't go away. And then we continue with the process we talked about earlier, our spacer sidewall, our mask, and we use the e-beam to write our layout with negative resist. The e-beam, because we have very small features. Our layout is basically a line across the graphene, and it's 50 nanometers by 20 microns. So we want it to be very, very, like, almost perfect. That is what the e-beam was going to help us with. We continue with our process. We get our spacer sidewall and our silicon nitride spacers. Now, like I said, ideally we want it to be 80 nanometers total, 20 nanometer spacers, and at least 20 nanometers. I know I started with 10 nanometers, but that would be just perfect. Unfortunately, I was only able to get to this part in my project, so I don't know exactly how close to 80 nanometers this is. But I would assume we got to about 100 because I did deposit 30 nanometers of nitride rather than just 20, just to be safe. So this would be future work. This just simply because I didn't get through the entire process, but our source and drain, this would be the area where it's exposed, so it's with positive resist. Therefore, we etch the silicon dioxide and the silicon protection layer to get to the graphene, deposit our metal, which is gold, and then we use liftoff to get rid of any other excess. And then we have our source and drain, and our back gate is in the bottom of the wafer, cleaning off any of the oxide and just adding the same metal as gold with a 1 nanometer of chrome as the adhesive layer. And that is my project. Do you guys have any questions? Yes. She asked me how thick the gold layer was, and that is 100 nanometers of gold and 1 nanometer of chrome for the adhesive.